Good afternoon, everybody. Sorry, we did not update for the past couple of weeks. We're doing our high school graduation. So now let's look at problem number 4, which is day 2, problem number 1 of the IOI 2022, which is digital circuit. The problem is like this. You basically have, just skip all the discussions. You basically have a tree. And on each tree, except for the leaves, the switch gates. Each switch gate has certain threshold. If you have the child of this node, this switch gates that has number of child that are ones that are at or more than this, then you can turn this on. So for example, in this case, let's say those two leaves have 1. And then say this threshold, this switch gate has threshold of 1, so you turn this on. And this gate has threshold 2, so you have 1, 2 of the child, so you turn this on. And this one, let's say, has threshold of 2, but you only have 1 child. That is 1, so you cannot turn this on. Okay, so that's the thing, right? Then the question is, you have to give you a boundary of the range of the source gate, where the state is triggered, then return the number of ways assigned to the parameter to the threshold gate, which will result the final gate has threshold of 1. So how many ways you can basically, if I change the leaves, right? How many ways you can make this to be 1? Okay, so that's basically the problem. Let's look at some of the subtasks. Let's start with, subtask 1 is too easy. Let's start with subtask 2. Actually, let's just start with 3. 1, 2, 3, they're more or less the same, right? So start with 2 first, because it has each threshold gate has exact 2 input. That means it's basically a binary tree, right? A full binary tree. So if we do 2 DPs, let's say DP0 and DP1, okay? DP0 of a node is the number of ways to make this node value equals 0. DP1 is obviously a number of ways to make this node the value of 1. So we can, this is a classic question to do DP over the tree, right? So we can say DP of 0 of this node, right, is if you want to make this 0, right, number of ways to make this 0 means, because it's a binary tree, right? It's a binary tree. And so you make this 0 and this 1, or you make this 1 and this 0, or you make both this 0 and this 0, right? So that's 3 ways to do it. So it's dp0 on the left times dp1 on the right plus dp1 on the left, times dp0 on the right plus 2 times of dp0 on the left of dp0 on the right, right? So DP1 is very similar, right? So basically is 0 on the left, 1 on the right, plus 1 on the left, 0 on the right, plus 2 times 1 on the left, 1 on the right, right? I mean, just, I'm not writing here, but you know what I mean. So that's problem number 2. So the complexity is each time you do this, you have m plus n, and this q curious, that's the complexity. Okay. Problem number 2. That's an easy problem. Then problem number 3 is same as problem number 2, except it's not a tree. It has each node has a multiple. Each node could have multiple. So that means for each of this, we just do capsac, right? Cannot spell today. Capsac, right? Capsac DP. That's traditional approach, right? So you do because you have more than 2, you do capsac. Then that can be solved. So you have the same complexity, right? The complexity is the same. Okay, so that's task number 3. So let's look at the task number 4 and 5. For 4 and 5, m is 2 to the power of z. Okay, so that means it's a perfect binary tree, right? So each time you trigger one of the each time you update one of the leaves. So if it's a perfect binary tree, the depth or the height of the tree is log m plus n, right? So then if I just use the same dp, like the above, so because every time the only dp value you're going to update is the path that from the leaf, from that place you up to the node, right? Because L equals R, right? Because every time you only update one, right? L equal R, right? Every time you only update one leaf. So you have a tree, right? So you go from this leaf all the way up. That's the only thing you need to update, right? So then the time complexity is going to be n plus m plus q times log m plus n, right? Because every time you only update one branch. Okay, so same approach as above. Then problem number 5 is the same as 4, except I'm going to update the multiple leaves now, right? There's no m equal m now. Okay, so then suppose all the leaves in the trees are, like, say, in a subtree of a node V is updated, then we can just swap the value of, right, dp0 and dp1. We can do a lazy update, right, similar to above. Then we treat the whole perfect binary tree as like, say, segment tree, right? Because m equals 2 to z, right? It's a perfect binary tree. So then it's have the same complexity as this, right? So now we'll get to a little bit difficult problem now. Problem number 6. It's a binary tree, but it has but it has no, we remove all the limitations. Okay, let's see. How do we do this? Right? So first, if you've noticed that when we do the dp0 of v plus dp1 of v, this sum is fixed, right? Regardless, this sum is fixed because it covers all the possible states of this subtree, right? It covers all the possible states. So this sum is a fixed value. It doesn't matter how you're going to change it. So then this actually equals 2 to the power of size of v, right? Because it covers all the combinations. So then if we look at it, so then if we look at the dp, if we take the above, let's write it down. dp1 of v, we said is dp0 of left times dp1 of right, right, plus dp1 of left times dp0 of right plus 2 times. So if let's take the 2 times break into, because it's 2 times, I write it twice. dp1 of left times dp1 of right plus dp1 of right, dp1 of left times dp1 of right. I'll write it 2 times, okay? So the reason I write it 2 times is if I take, this term together, so it's dp1 of left times, right, dp0 of left plus dp0 of right plus dp1 of right, which is this, right? 2 times size of right, right? And again, if I take dp1 of right, right? So then this and this add together, right? So it's dp1 of right times 2 times size of left, right? So now this is interesting because it turns out the state of dp1, basically the number of ways to make this node equal 1 only depends on the child state, which is also 1, right? It does not depend on 0 anymore, right? Only depends on 1. So then that means this switch is an operation only on the value of its child. Right? dp0 is only depends on the zeros. 1 is only depends on ones. This is some kind of operator. Right? This switch gate is some kind of operator. So then we can, for each leaf as state of 1, we can count how many ways from it to reach to the root, right? That's what we can count. So then the number of way to reach to we know the number of way to reach from here to the root is 2 to the power of n minus the depth of v, right? So if its state is 0, it doesn't contribute. The leaf doesn't contribute anything. If the leaf state is 1, it contribute this much times of this thing. So then you can do range update, right? Just like a segment tree. So that gives you complexity of m plus n plus q log n. Right? Okay. So this interpretation is very important. Okay. Now we look at 7. I mean, 7, 8 is the same thing. I mean, just basically know if I can solve 8, I can solve 7, right? So then as we said, for each leaf, we can look at all the way from the leaf to the root, right? And compute the product of the number of child for the internal node, right? So we can do it this way. For each node of V, right? So let's say we have a tree. For each node of V, we can compute the product of number of child for all the nodes in the subtree, right, of the V. Let's call it sub of V, right? But for each node, I mean, excluding the leaves, we can count, let's say, excluding the leaves, we can count for the subtrees, we can all the products of number of child, right, all the internal node. So that is done by O of n. Then we need to count the contribution of all the leaves, right? We can do it as a DFS, right? We do it DFS. When we travel to the child of a node, you can compute all the subtree values for all the child, right? From all other child to the final product. So we can, let's say you have a child U1, U2, all the way to UX, right? So then you can count the prefix of this for each chart. The chart, you can count product of this, product of that, right? Then you just travel through the chart, right? So then you can calculate all the subs. Okay, so once you do that, then do DFS, you're gonna get the result. Right? So that will give you the same complexity as this. Okay, so that's how you solve it. Then this subtask is actually quite important. The way to organize the subtask, it actually gives us a hint along the way. Right? We first started with this DP because that's how it's a classic problem, right? Left and right. Then we start to realize because zero state and one state, the sum of that is basically covers all the possible states. So it's 2 to the power of the size of V. Then you derive it, you see it only depends on itself. It doesn't depend on the other. Then you can figure out, oh, then I can just count from the leaf up, right? The number of ways. Then the way how to do it is you can do DFS, and every time you do DFS of the child, then you just work, right? Count the prefix product and suffix of product, then you just work through the child. So that's how we solve the problem. Okay. So it's not a very difficult problem until when you realize this thing. Right? It only depends on the state of V, total state of V, only depends on the size of the subtree. Okay. So that's problem for today, this week. Next week, we're going to talk about problem number 2 of day 2, which is the insect. Okay, the insect problem. Take your time, right? So I think for most people, as hopefully for everybody, is summer break. So take your time to solve this problem, and we will see you next week.